Hello, everyone. I'll talk about our research on leveraging graph representation learning to predict harmful application installation on mobile devices. This is a joint work with Gianluca from Boston University. Here comes the overview of my talk. I will start with motivation. Then I will cover technical details of our proposed approach. I'll briefly touch the experimental results and discuss the limitations of our method. What you should see here in this slide is a typical timeline of PHA installation and removal. So for example, at timestamp T1, you have a device that has a couple of these PHA installed. So for some reasons, the users install another new PHA, and at time T3, the user remove it. If we look at the timeline into two parts, so before PHA installation, let's say before timestamp T2, we may rely on a couple of methods like Google Bouncer, Google Play Protect, and market policies to remove PHAs before they even being offered to the end users. Did the research on the distribution vectors of PHAs and published in S&P this year. Please have a look. And if we look at the timeline, like after the PHA installed, we may rely on the antivirus products to remove, basically to detect, then remove the PHAs. However, due to Android security architecture, it requires consumers explicit permission to remove PHAs. That means the antivirus products are able to detect the PHAs and send the warnings to the end user. And the end user has to explicitly say, yes, I want to remove this PHA, then this application will be removed. The consequence is that between the detection time, let's say time T2, and the removal time T3, it creates a window of opportunity. That means the PHAs are on your device and they can actually connect your data and do other sort of the things. That's why we propose ANDRUSPEX to position the system before the PHA actually being installed by the end users. And you have the question that why don't we just rely on the Google Bouncer or Google Play Protect for market policies? So apparently the conclusion from my colleague is that they are effective, but they're not enough. So that's the motivation of ANDRUSPEX. And the purpose of the prediction system is to warn the end user in advance of what PHAs they might encounter in the future based on the current security posture of their devices. So what are the challenge to devise such predictive method for the mobile devices? I think the first thing is that if we only predict based on the per device perspective, the data is reasonably sparse. So for example, if we take the device D1 and we say, okay, D1 install a malware M5. So which malware or potentially PHA would be installed in the future? It's really hard just to, based on M1, M5, then do the prediction. So our solution is to aggregate historical information of how the PHAs have been installed by the mobile devices globally. If we look at the graph on the right-hand side, we aggregate all the information from all the devices globally and create a condensed structure. So in that way, we'll be able to offer better view of what is happening globally. And from there, we have two questions to solve. How do we do prediction using this global PHA installation graph? And how to devise a method that is scalable to a global PHA installation graph that potentially going to be reasonably large. Now, let us look at the prediction problem. Ideally, if we have data to do causality inference, that would be ideal. So for example, if you install PHA and we have the causal inference that you will install PHA-B, that would be an ideal condition. But we don't have such data to do causality inference. To solve the problem, we use random walk to model users random installation behavior. So for example, if the device D1 install malware M5, we just take a random walk along all the observed PHA installation path, and potentially, let's take this one for example, is that M5 also installed on D4 and D4 also install M3. And if our system would model this random behavior, we would just propose that you may actually encounter PHA M3 in the future. But does it make sense to use random walk to model that kind of random installation behavior? So we did a analysis is to understand the PHA degrees, which is the installation events, and its average degrees of all nodes that's reachable by all these PHAs by 2 and 4 hops. So if 2 hops, that means it will be hopping on to a different device just next to it. On the left-hand side, you will see the 2-hop example. And 4-hop means that M5 to D4, then to M3, then to D2, then to M2. So that is 4-hop, basically a path length 4. And we figure out that the PHAs with larger installations, that means the PHA is presented in a large number of devices, they coexist with smaller ones, like less popular PHAs. And second thing is like, the more hops I take, the correlation coefficient decrease between the PHA degrees and the average degrees reachable by 4 hops comparing to 2 hops. So how do we model this behavior then? So what we do here propose is like, if we take the left-hand side installation graph, for example, and take the random walk length along the axis, you'll be able to see that the larger the random walk length is, the more information will be filled in the matrix. But at the same time, potentially, it will actually add more noise to the system. We propose to use random walk approximation to approximate the matrix factorization. The key goal of matrix factorization is to get the node dimensional representation of the device node and the PHA node. And we concat these 2 vectors together and represent as an edge. And the edge is actually a PHA installation event. But again, the question is, does it make sense? So what we do here is to visualize it. We visualize the observed PHA installation as blue and the non-observed one as orange. So we use large vectors to project these vectors into 2-dimensional space and visualize it. You can see that this method we proposed is able to distinguish between the observed PHA installation and non-observed PHA installation. And more details you will find in the paper. And here is actually the pipeline of our system. So basically we have the raw data, then we build the PHA global installation graph using the raw data and use the matrix factorization to get the node dimensional representation of node, and then concat them together to get the edge representation. And then we use a binary classifier to tune the system, so we will be able to predict in the future, given 2 nodes, device and malware, whether or not there will be an edge between them. If there is an edge, we say potentially you will install that in the future. Then we evaluate the system using 31 days of PHA detection data from our company. We cover 3 scenarios: 1-day prediction, 1-week prediction, and 1-month prediction. And we strictly require that the training data is not overlapping with the test data. So for example, if we use a user's historical information to do the 1-week prediction, that means we will use the first 6 days historical information to train the model and to predict the device's installation behavior on the 7th day. That's the setup of our evaluation. So the precision is pretty good. Our system is able to achieve high accuracy given different level of false positive rate. There's one key thing to observe is that high false positive rate leads to worse experience because you generate too many false positives to the end users and potentially lead to high customer churn rate. I mean, the customer will leave in your service. That's why we choose extremely low false positive rate, and our system still achieve high precision. And from the practical perspective, a key thing we need to deal with is the data latency. Data latency means that the data will not be telemetry data will not be delivered to the backend system on time because of different reasons. For example, the user just turn off the telemetry, or the user is actually using the mobile network, and we won't connect the telemetry data unless the customer is actually using Wi-Fi. So all sorts of the practical reasons we have to deal with data latency real. And you will be able to see here, like take data set 2, for example, the 1 week prediction, we will be able to achieve good performance. Even the data latency is reaching about 25% of the total data. Now I move on to the limitations. And the first limitation of this system is node attributes are not involved at the training or testing phase. That means we won't get we don't use the device information, we don't use malware information. So in the future, next generation system should be able to use them to do a better representation learning. And second limitation is that we put the system in a transactive setting. Transactive setting is like the global installation must be rebuilt every time. If there's a new PHA, the and since this is a new installation graph, because introduction of the new PHAs and the model has to be retrained. So that's the limitation of the transactive setting. One way to compensate that is that the way we train the system is pretty fast. So we will be able to do the frequent retraining on a daily basis. And the third limitation is obvious, is that we can only predict known PHAs. We won't be able to predict previously unknown PHAs. And the final limitation is from the usability perspective, is that how do we devise effective notification system to warn the user that based on your installation history, you will probably likely to install PHAs in the near future. And the current notification system is like notification bar is less effective. And that front, we don't have user study, so that will be the fourth limitation. And this concludes my presentation, and thank you for your time.